Okay, good day, everyone. So a quick announcement. I sent out an email about the exam number 1. So it will take place next Friday. That means your homework from chapter 2 and chapter 1 and 2, right, is due on Friday. So again, you should try to complete your homework either in a Word file or Excel file. And if you want to convert it, to the PDF file, you can do that. But you can submit it either as a Word file, Excel file, or a PDF file. Also, next.
I have a quick question.
Areta, yeah.
Your email says that the exam was, you said next Friday or this Friday?
Next Friday is March 5, right?
Oh yeah, March 5. Okay, I was confused. I suddenly thought it was this Friday. Okay.
Okay, definitely. I told you guys I'll give you a week notice, so I will usually do that. I'll give you a week notice for all 3 exams, so you can get ready for that. And any questions about the exam number 1 and the homework? Okay.
For the exam number 1, is it just gonna be like what we learn in the chapter, or like throughout the chapter?
Yes, it's gonna be similar. I was about to talk about that. Yeah, that was a really good question, Yasmin. So you go to our homework, our Blackboard course, right? So then you click on review for the exams. So the review for exam number 1 has been, okay, let me post it now. Let me make it available so you guys can look at it first. Don't forget to make it available. Okay. So now your exam will look similar to the review sheet, right? So if you open it, doesn't allow me to download it. Let's see. It should be a Word file. I created in a Word document. Yeah, I can open it. Okay. And your exam is about 10 questions, right? Just like, so to go over the review sheet, right? It'll give you a very good idea, what do you expect on the actual exam. And any question on this?
Is it gonna have any Excel stuff on it?
No Excel. It just all these word problems, like your homework question, right? It's very similar to your homework question. Yeah. So if you do well on your homework questions, you will do well on the actual exam, right? Yeah. So we're gonna go over this review sheet next Wednesday, right? So, but I really want you guys to try first before next Wednesday. So give some time next Monday or Tuesday, go over all these questions on your own. And if you can easily, or if you feel comfortable doing all these review questions, that means you are ready for your actual exam. Okay. And again, during the exam, I will ask you to, I will put you in the breakout room, and also I'll ask you to open your camera, right? Okay. And then also you can complete your exam in a Word file or Excel file. So definitely totally up to you, right? You can just write answer in Excel. Yeah, and then submit the Excel file. I'll create Dropbox for you to submit your the work for the exam number 1. Okay. All right. Any other questions beside this? And today and then Friday, we have one more important topic, right? 2 more important topics, actually. Graphing the exponential functions, and also application of the exponential functions. It's going to be on your exam number 1. Okay. So if you have no other questions, I'll get started on those 2 topics today. Okay, very good. So I'm going to open the PowerPoint. I had a brief introduction on the exponential functions last Friday, and we continue from there. Okay. All right, we talk about how to graph a simple exponential functions. Then we actually already graph this one, and we try to graph this one. Yeah. So again, we get some order pairs, right? Minimum 5, and then the more order pairs you have, the better it is. So in terms of graphing this, minimum 5 order pairs.
Professor,
Yep.
I can.
share
Are
that.
you showing?
Yes,
Yeah.
yes. I haven't shared it yet. Sorry. Yeah. Here we go. Can you see it now?
Yes.
Okay. Okay. Very good. So this is from the PowerPoint, right? From section 2.1, 2.2. And last time we actually went over how to graph h of x equal 3 to the x. And as I mentioned, whenever you plot in an exponential function in a Cartesian system, you need 5 order pairs, right? 5 points order pairs, meaning 5 points minimum. Okay. Typically, some textbooks using 7 points or 7 points. The more points you have, the better it is, meaning you have a more accurate graph. Okay. All right. Yeah. So this comparison between g of x equal to 2 of x, 2 raised to x power, h of x equal 3 to the x power. As you can see, 3 to the x power actually increase much faster on the high end. Meaning on this end, this red curve increases much faster because the base is bigger. So the base determines how quickly the exponential function grows, right? So when this base is greater than 1, the bigger the base, the quicker, exponential function increases when x value is bigger than 0, right? Bigger than, yeah. Exponential function increases much faster when x is greater than 1. Okay. All right. So basically, there's just some base property. You can observe the different type of exponential functions and get this general property out of it. Okay. Yes. Let me just erase this, and then let me just explain this really quickly. So exponential function with a positive base greater than 1, the graph are increasing, right? They're both increasing actually. And when the base is bigger, then it's increased much faster when x is greater than 1. And the function never crosses x-axis because x-axis is what we call the asymptote. X-axis is what we call asymptote. And asymptote is a line or curve. The function gets infinitely close but never touches it. Okay, so that's the most important thing about asymptote. Okay. Now, yeah. The PowerPoint acting a little bit weird today. But yeah, I try to slow down a little bit. Okay, so x-axis is what they call the horizontal asymptote. Right? Okay, and there's no vertical asymptote because it's increasing indefinitely, right? For both functions here. And also the smaller base means the graph rises more gradually, meaning less rapidly compared to the bigger base. A larger base means the graph rises much quicker, right, compared to the smaller base. An exponential function will not have negative base, right? So the base is always positive. So base always positive. Now, let's look at another type of exponential function called f of x equal to e to the x. So e here is called a natural number or Euler number. E here is called natural number. And it's named after a Sweden mathematician called Euler, right? Euler. It's a very famous mathematician in math history. And here the E is approximately equal to 2.718, 28169. And it has infinitely many decimal places, just like pi, right? Pi is approximately equal to 3.1415196. Very similar concept. It goes on forever. Same thing for E. And later on, I'm gonna guide you guys in Excel how to generate this natural number from some Excel operations. Okay, I will show you in a bit. You can also get it yourself. So natural number E come from this process. It's called limit. And when x approaches 0 for this. Also, you can also do this. So this is one way to do it. Another way is the limit when x approaches infinity for 1 plus 1 over x to the x. So these two actually give us the same result. So I'm going to stick with this one, okay? Because this one actually it's easier to operate within Excel, okay? So it's limit when x approaches infinity for this particular function, right? And basically we can come up with this. So now let's open Excel, okay? Now I want you guys to open Excel, and then we're gonna run through a series operation to get this Euler number E in Excel. Okay. So you just follow my direction, right? So I'm gonna go through this step by step, and you can just follow what I did in Excel, and you'll be able to see how the Euler number was generated, you know, in a theoretical basis. Okay, so let me share the screen with you. Here we go. So let's open Excel really quickly. And we're going to do two things, right? We're going to have x values. And we're going to have this function called 1 plus 1 over x and raised to x power. Okay. So these two columns, and then we give you some numbers, and then we can just feed in this table to get the idea, you know, how this Euler number was proved. So let's start with a relatively small number, right? So let's say, since we know that x approaches infinity here. Okay. So when x equal to 100, so we're just gonna plug in this. So we put an equal sign here. All right, we're gonna do 1 plus 1 over this number, right? Whatever that number is, and then raised to a power. Okay, B3. Okay, and we get a result. You see that? Now, if you let's say we put in 1,000 now, so let's generate all the numbers based on this pattern. Now that increase by 10,000. Okay, so every time increase 10 times. No, it doesn't generate. Okay, so 100,000, a million, and 10 million. 100 million. So, a trillion, right? I guess we could just stop here. Yeah, that's a trillion. Now, similarly, just input this, and now you can just drag this, get the rest of them. As you can see, when the x value keep increasing, you know, this result getting close to the Iola number, right? This number is look very, very close to the number we have in our PowerPoint. So this is how the Iola number was generated, also proved by this limit process. And then x approaches infinity, meaning the x value gets bigger and bigger. Okay, so that's how that goes. And the other one is the other method is just this. Okay, the other method is using opposite process here by looking at when x approaches 0. So in the opposite direction. So now it just becomes 1 plus x and raised to 1 over x power. We can also do that in Excel really quickly. So here the number will become getting smaller and smaller, right? So for example, let's say we're getting 0.1, right? And 0.0, that's too big. Okay, 0.01. Okay, that's 0.001. Okay, that's getting closer to 0. Yeah, okay, 0.0001. All right. Approaches 0, negative sign, positive sign. Okay. So here I should modify the formula a little bit, otherwise the result wouldn't come up. So here we go. I'm going to delete this. Let me share the screen with you. Okay, so this is like opposite direction, and let's get more numbers here. Again, as 0 increases, that means this number is getting closer and closer to 0. That's one more. Yeah, here we go. So now let's calculate this. So it will be equal to 1 plus this number and raised to 1 over this number, G3. Now, once we have that, then we just hit enter. Now you can just drag this and get the rest of them. As you can see this number getting closer, right? They converges. You can even match them a little bit. You see, match them. This number matches with this, right? This number matches with this. So that means using both methods here, the second one is when x approaches 0. We generate the Iola number. Okay. And actually, the two methods provide same result. That means, yes, Iola number was generated in this particular process. It's called a limit process. So that's how we prove the existence of this number, and then also prove the value of this number. So as the number gets infinitely many large here, then this number becomes very stable, right? Becomes a very stable number without varying too much. Okay, so that's how this E was proved in a theoretical basis. And this base E is also very important exponential functions here because it has a lot of applications in the real world, like the population growth, like the compound interest, right? They all use this very important concept. Okay. For some reason, the PowerPoint wasn't responding, so I have to reopen it. Okay. And in your calculator, you should be able to find the E, right? The base E in your calculator in terms of graphing this, and it's very important, to use a calculator because the number is quite large. There's a lot of decimal places, so you wouldn't be able to do it by hand, right? It would take a long time to do that. So that's why we're going to use a calculator to perform this calculation for exponential function with base E. Okay. And this is the process. We just I just demonstrated in Excel. If you want me to post that Excel file, I can do that after class. And this is the Sweden mathematician who invented Euler number, who discovered that, right? It's called Leonhard Euler. Okay, so this is the mathematician who discovered this Euler number. So now let's take a look at how we graph a exponential function with base E. So basically, it's very similar to the other exponential functions. We just have to generate.
Professor?
Yes.
Are we supposed to be seeing something? Because
yeah.
I
Okay, no problem. I probably forget to share the screen again. All right. Yep, you're supposed to see this. Yeah. Can you see the PowerPoint now?
yes.
Okay, very good. So we just went over this Swiss mathematician called Euler, right? He's the mathematician who discovered this Euler number. It's all, yeah. And let's look at how we graph this exponential function with base E. So E is approximately equal to 2.718. Right, and we can just use typically if you do a rough calculation, 2.718 should be enough. But and if you want a more accurate answer, you should put into the calculator to get a result. So here we're going to pick some values from -2, -1, and let's calculate 0, 1, 2, right, 5 order pairs. And let's calculate what is f of -2. But this is f of x, so that means it's x becomes -2. So this is e raised to -2nd power. So you go to the calculator, find the exponential function with the base E on your calculator. If you're using TIA 30X I recommend it to you. You should use second and then LM, right? You get an E, and then raised to 2nd power -2. And it becomes 0.14, approximately 0.14. Make sure you can get this number from your calculator. If you run into 2 decimal places, so it's approximately 0.14. And second order pair is f of -1. So e raised to -1st power. And again, you put into the calculator. And you get that 0.37, approximately 2 decimal places, 0.37. And the third one is f of 0, e to the 0 power. That should be 1, right? Because that's exactly 1. Okay. And then fourth one is f of 1, e to the 1st power. That should be approximately 2.718, so it's 2.72. Okay. approximately. Okay. And e f of 2, e to the second power is 7.38, but let me double check. E to the second, that turned out to be 7.39 approximately. Okay, now you have 5 ordered pairs. Now we'll be able to sketch the graph. And as you can see, 2, you see this is 7.39 somewhere here, right? This is first, this last order pair. So -2, it's this. Okay. And then -1 is 0.37 here, and 0, 1. Next order pair 0, 1 here, and then 1, 2.72 somewhere here. Here. All right, so now you have those 5 order pair connecting, then extending in both direction, then we get this exponential function of base e. And also, x-axis is still the asymptote, horizontal asymptote. Meaning this curve, this exponential function gets infinitely close, but never touches it. Okay. It's x-axis here, y-axis. Okay, and that's how you graph this exponential function of base e. Right? Okay. Any question on this? All right, so now let's look at this one. Okay, so j of x equal half of x, and still now the base is less than 1. And once the base is less than 1, actually behave slightly differently. So we can just come up with all those numbers first. So j of 2 first, right? So it'd be half to the second power. Then that's quarter. 1 square over 2 squares, quarter. That turned out to be 0.25. And when it's half, so basically what it's saying is the number becomes half every time when we when we increase number by 1 unit, right? So a quarter. So the j of 1 is half to the first power. That should be half. So it's 0.5. And we get that. And then j of 0 is half to the 0 power. In number to 0 power is 1. So this should be 1. And j to the negative first power, that should be half to the negative 1 power. Reciprocal this number becomes 2 over 1 to the first power. 2 to the first is 2. So the result is 2 there. And the very last one will be 4. Okay. J of -2 is half raised to negative second power. Again, reciprocal the fraction becomes 2 over 1 to the second power. 2 to the second, that's 4. Okay. Yeah, so we get all these order pairs. So as you notice, we put these numbers in a decreasing order, right? So it's decreased by 1 unit. If you if you reverse it, start with -2, -1, I think the pattern will be more clear here. So we rearrange it, right? From the smallest x value all the way to the largest x value. Then -2 becomes 4, and 2. Then it's 1. Then it's half, and it's a quarter. As you can see, since the base is half, now this number is becoming half, and half, right? So that's how you're making connection between the base and also the trend of the y values. Okay, So the base determines, how this exponential function moves. Either it's increasing or decreasing. Here, since base is less than 1, so the exponential function decreases, right? It becomes half every time when the x value go up by 1 unit. Now, once you graph it, it becomes this. So you're plotting all those 5 order pairs, you get this graph. Right? -2 becomes 4, -1 is 2, 1, 0, and then -1. Yeah, so 1 is half, and then 2 becomes a quarter. And once you have those 5 order pair connecting them, extend on both directions, then we get a graph of this exponential function with the base half. Less than 1, they are decreasing, right? From left to right, it's decreasing. Okay. Still, x-axis horizontal asymptote. That stays the same, but it's decreasing from left to right. So the base definitely determines, and we also call this exponential decay model because it's decreasing. When the base is between 0 and 1, yep, so we have an exponential decay model. When the base is bigger than 1, then it's an exponential growth model. Okay. And why do we study exponential functions? Because it has a lot of real world applications, right? Like measure growth, interest, and decays. Okay. And a very good example is population growth follows follow exponential pattern. Also the compound interest, human populations, bacteria, how the bacteria grows or decay follow the exponential function pattern. Computer technology, nuclear chain reactions, and also very important concept in finance, compound interest. They all follow the exponential model, right? That's why exponential function is very crucial to understand a lot of phenomena in our real life. And section 2.3 is exactly the application of the exponential function in terms of measuring the human population growth, right? So we're going to take more close look at that particular application in a bit. Okay. Yeah, and also we have this is all growth, right? We also have a decay, like nuclear, nuclear, chain reactions also for decay. And carbon-14 dating, half-life, Newton's law of cooling, all of those follow exponential decay models. Also, like once the nuclear reaction happens, all those important elements becomes decay, right? Meaning it start to decrease on a constant basis. Yeah, so and this is introduction on that. And let's go back to the textbook. In the textbook, there are a lot of interesting questions. Let's go over some of them. Okay, so now let's open textbook. Now we're going to go over some of the actual problems in your textbook. And let's turn to section 2.1. Let's start with some of the graphing problems. And let's type in 30, page 30. Probably 45. Okay, it is. This is 2.1. It's graphing all those different exponential functions. Yeah. So let's create this is exercise 2.2. And let's look at question number 2, right?
Can you share your screen, please?
Yeah, sure. Yeah. And you can also open your textbook. Yeah, this is on page 46 on your textbook. And we're going to take a look at how to graph question 2, right? F of x equal 3 times 2.3 raised to 2x power. And we're going to go over all these even problems to help you get started on this. Okay. So question 2. Maybe just print screen. And I'll go over that step by step so you'll be able to easily follow all these procedures. Okay. So question 2, f of x 3 times 2.3 raised to 2x power. Okay. So now the base is 2.3, right?
Wait, can you share it again?
Yeah. Okay. Yeah. Here. It's here. Okay. Yeah, so base is 2.3. And then also we have coefficient. Coefficient is 3 in front of it. So that means it's 3 times as much of that exponential function. So now similarly, we're gonna need a 5-order pair. Okay. I'm gonna pick some on the left, pick some on the right. Follow the same pattern, I'm gonna pick -2, -1, 0, 1, 2. Okay. So now from there, we're gonna calculate the y values. So f of -2 first. So this is 3 times 2.3 raised to 2 times -2. That will make it -4. So this is actually 3 times 2.3 raised to -4th power. So again, you don't have to do it by hand. Put it into the calculator or Excel, get a result. And that's why that Excel practice is very important, because we're going to encounter some of the difficult, exponential functions, and then you need those calculation skills. And this turned out to be 0.11, right? Let me quickly show you how to do this in Excel. Just a quick review on that. So you just do share the screen. Okay. So you do 3 times 2.3, close it, raised to -4th power. And typically, if it is negative number or more than one number, you should put into the parentheses to be safe, right? And if you enter, you get this. If you sort it to 2 decimal places, run it to 2 decimal places, you get 0.11. Okay, and that's how you do that in Excel. So 0.11, that's the answer for this. Okay. Now f of -1 will be 3 times 2.3 raised to 2 times -1st power, and this is 3 times 2.3 raised to -2nd power. See what that is. Now that turned out to be 0.57. All right. Now f of 0, this will be 3 times 2.3 raised to 2 times 0 power, and this is 3 times 2.3 is 0. Any number raised to 0 power is 1, so it's 3 times 1, that becomes 3. Now notice that this number is not 1 anymore. Why is that? Remember, for all that exponential function we talk about so far, the y-intercept is always 0, 1. Why this one is not 0, 1? It's 0, 3. Anybody figure out the answer for that? Notice the coefficient is 3. So it actually increases all these number 3 times, right? So all these f of x, the y values become 3 times as much. So instead of having 0, 1 as a y-intercept, now it becomes 0, 3 because of this coefficient. And f of 1 is 3 times 2.3 raised to 2 times first power, so 3 times 2.3 to the second power. Let's see what that is. And this turned out to be 15.87. And this is the exact answer, so 15.87. And f of 2 is 3 times 2.3, should be raised to a 4th power. 2 times 2, that's 4. 3 times 2.3 raised to 4th power. Let's see what that is. You can try in Excel. So this is 83.95, approximately 83.95. And once you have this, you sketch this. So we have 5 order pairs. We can sketch the graph. So put into the order pair. So first one is negative 2.11. So it's wide. It's very wide change. As you can see, when the base is greater than 1, and the coefficient together with the coefficient which is bigger than 1, and this exponential function grows at a very rapid pace. So 0, 3, 1, 15.87. From jumping from this 15.87 to 83.95, that's very quick jump to it's 83.95. We have 5 order pairs and we can sketch the graph. You just have to plot those numbers. So picking the proper x values. Yes. That's very important to getting a good graph. So this is negative 2, negative 1, 0, 1, 2. On the vertical axis, we need all the way up to 90. So this each unit represents 10. So this is 10, 20, 30, 40, 50, 60, 70, 80, and 90. So graphing by hand will be, you just have to pick the this XY values very carefully. So now let's plot in the order pairs. So negative 2 become 0.11, so it's very, very close to the x-axis. You can also try yourself on your paper. Okay. Well, so we start with negative 2 and 0.11. So it's down here. And negative 1, 0.57, no big change, right? And 0, 3. 3 should be somewhere here. That's third order pair. 5 is here. 3 is underneath it. Okay. 3 is here. And then 1 is 15.87. So it's it's somewhere in the middle of 10 and 20, but slightly bigger than 15. So 15 is here. Okay, slightly bigger than that. This is 3. And then 2 is 83.95. 83.95 is all the way on the top. Here. Okay, now once we have those 5 order pairs, now we have to connect them with the curve. And again, the x-axis is still the asymptote, so it never touches x-axis. Okay, and that's how you sketch an exponential function, a slightly more complicated exponential function. 3 times 2.3 raised to 2x power. Okay. Any question on this? All right, we can easily verify this in Excel, right? You can quickly get an Excel graph for us. Okay, I'm going to do it in the second page. me share the screen with you. There you go. So we have this x, and then f of x is 3 times 2.3 raised to 2x power 2 times x. So we just need to create order pair first, 5 order pairs. And format it a little bit. Center, bold, borders. Okay, so the number is -2, -1, 0, 1, 2. Okay, have that, and then let's calculate the y values. So it should be 3 times base 2.3 and raised to 2 times this x values. Okay. Once we get one of them, yes, we can get the rest of them really quickly. Okay, and again, we're running 2 decimal places. Now you're gonna see we're gonna have exact same numbers like what we did by hand. Now I'm just gonna sketch the graph, go to insert, scatter plot, get the scatter plot first. And just resize it a little bit so you can see the graph. Okay, now we just fill in the here under trend line, we're going to fill in the exponential model. As you can see, this is what the graph look like. No options. Okay, fill the exponential model. Display the equation. You see, yeah, no, it shouldn't be a proper one. And I guess I'm putting a solid line. Yeah, so that's pretty much how you do it in Excel to confirm, just to confirm what we have, right? And then we have exact same result as how you do it by hand. Okay. Yeah, okay, let's go back and let's take a look at another question here. So question number 4, I think I'll skip it, right? It's half of x. It's presented in the PowerPoint already. So let's take a look at question 6. Okay. With r of x equal 3 plus 0.87 raised to -2x power. Now here, you look at it, base is 0.87. So the base is between 0 and 1. So we know that it should be an exponential decay model. But let's take a look at how we graph it by hand first. Yeah, so we're looking at question 6 now. All right, let me share the screen. So r of x, can you see the screen?
Yes.
Okay, very good, thanks. 3 plus 0.87 and raised to -2x power. Okay. So now, actually, if you rearrange this, it probably makes slightly more sense. It's 0.87 raised to -2x power plus 3. So this adding 3 in the back will vertically shift this exponential function 3 units up, right? So this is what the effect of adding 3 in the back. But it's okay. We can just, and that also changes horizontal asymptotes. So now instead of horizontal asymptote as x equals 0, horizontal asymptote should be x equal to 3 because it's adding 3 in the back. So the horizontal asymptote also being shifted 3 units up. So x equal 3 is horizontal asymptote. Keep that in mind. You're going to see that from the graph once we get in these order pairs, x and r of x. Similarly, I'm still going to stick with the same number, -2, -1, 0, 1, 2. same numbers. So now that we just have to find all these y values, r of x. Right? Okay. So r of -2 should be 0.87 raised to -2 times -2, adding 3. So -2 times -2, that become positive. It become positive 4. So it's 0.87 raised to 4th power. Okay, so it's 0.87, 4th power adding 3. So now, similarly, you just have to put into the calculator or Excel to do the calculation, adding 3. So here we go, we get 3.57 approximately. So the first y value is 3.87. 3.57. The y value for the first x value, and then f of -1, and r of -1. Okay, all of this is in the function notation. R of -1 should be 0.87 raised to -2 times -1st power, adding 3 in the back. So this is 0.87 raised to 2nd power, adding 3. So let's see what that is. And that's 3.76 approximately. As you can see, all three, see, because adding 3 in the back. Originally, if it's just 0.87 raised to 2 to the x, it would be 0.57, 0.76, but we're adding 3 in the back. So out of 0, there should be 0.87 times -2 times 0, adding 3. So now on 0.87 to the 0 power, we know that any number to the 0 power is 1. 1 plus 3 gives us 4. Okay, so we got 4 here, 0, 4. And then R of 1, 0.87 times -2 multiplied by 1, adding 3. Okay. Then it's not to be 0.87 raised to -2nd power, adding 3. And let's see what that is. It'll be bigger than 4 then. 0.87 raised to -2nd power and adding 3. That's 4.32 approximately. And then R of 2 should be 0.87 raised to -2 times 2, adding 3. So this is 0.87 raised to -4th power, adding 3. And let's see what that is. Should be bigger than the previous number. So here, well, this is 4.75 approximately. So now once we have all those 5 order pairs, then we can sketch the graph. So now let's sketch on the side. So the x value still remains the same from -2, -1, and then 1, 2. And then on the y value, right, the minimum is 3.57, the maximum is 4.75. So in that case, I'll make it slightly bigger units: 1, 2, 3, 4, 5. Start sketching this. -2 corresponds with 3.57. 3.5 is here. Different color. This is 3.5. So 3.57 should be slightly above it. Okay, so here. And -2 is 3.76. -1 corresponds 3.76. So again, slightly Okay, 3.75 is here. Okay, and then 0 corresponds with 4. See, then we have 1 with 4.32. It's right here. And then 2, 4.75. It's all the way on top. Now, if you connect those, you see this is what we call asymptote here. So this curve will look like this. Just connect them with a curve extending in both directions. Okay, and the exponential function look like this. Okay, from left to right, it's increasing. Okay, label this r of x equal to 0.87 raised to negative 2x adding 3. And the reason why this is increasing, right, from left to right, you can do a little bit algebraic manipulation, do 0.87 raised to negative second power, then raised to x power, adding 3. And 0.87 raised to negative second power, that will become a number bigger than 1. And it becomes 1.32. 1.32 approximately 1.32 1178491 to the x power. Now it makes sense, right? That's why it's increasing from left to right, because the base is bigger than 1. Okay. That's why from left to right it's increasing. I'm adding 3 in the back, shift up 3 units. So this jumping from here, vertically shift up 3 units. So that's how we get a graph. And I'm going to also quickly show you how to get it done in Excel. Okay, here I'm going to have a new sheet. So now a couple of things, x and then r of x. R of x is 0.87 raised to 2x power, negative 2x power, and then adding 3 in the back. Okay. Okay, we need 5 order pairs, exactly what we have over there. Center. Did I forget to share? Okay. Yeah. Okay. So now similarly, we put in the same number, negative 2, negative 1, and 0, 1, 2, right? That's the number. Okay. Now we do the calculation. So it's 0.87 raised to negative 2 times this cell, B3. Okay. And then in the back, adding 3. Okay. You just have to calculate one of them. You enter, get that, and then just drag it all the way to the bottom. And you can see, if you run through decimal places, you can see exact same thing as what we, as how we did it by hand, right? And once you have those 5 order pairs, then you can just sketch it using insert, scatter plot, even better. Yeah, you can even do that, right? Just get a curve right itself. And then x equals 3. Okay, that's what we call the horizontal axis. Okay. Yes. Okay. And any question on this part? And the function may become slightly more complicated, right? Just but you can still stick with the same method. Just get those x values and then calculate the y values, and then you always get a graph right. Okay, let's go back. Yeah, question A is e to the x, and then we actually went over that. And we're just gonna go over to question 10. Okay, question 10 is 2 times e to 2 minus x. Okay, let's see how we graph that. Okay. And again, go to this. I'll do it by hand first, and then show you how to do that in Excel. So question 10, f of x equal to 2 times e raised to 2 minus x. So still very similar. We just gonna use, so here the coefficient is 2, right? Then base is e. Okay, so x f of x. 2, 3, 4, 5. So we're still picking the same number, -1, -2, 0, 1, 2. Okay, it always works. Okay, and we start calculating all these y values. So f of -2 should be 2 times e, 2 minus -2. Okay. And let's see what that is. Let's simplify first before you put into the calculator. 2 minus -2, that becomes e to the 4. So it's 2 times e to the 4th power. And let's see what that is. It should be a fairly large number. So 2 times e to the 4th power. I'll get 109.2. Okay, 109.20. If you want you to do that in more places, keep it consistent, it's 109.20. Okay, and f of -1 should be 2 times e, 2 minus -1. So this is 2 times e raised to 3rd power. Let's see what that is. And this turned out to be 40.817. So it's 40.17. Third order pair is f of 0. So this should be 2 times e, 2 minus 0. And that should be 2 times e to the 2nd power. Let's see what that is. And this turned out to be 14.78. And f of 1 is 2 times e to 2 minus 1. And that will become 2 times e to the 1 first power. And this turned out to be 5.44. 5.44. And then let's move down to the last one, f of 2. This will be 2 times e, 2 minus 2 becomes 0. So 2 times e to the 0 power is 2 times 1. E to 0 is 1, so it's 2. So this one is exactly 2. All right, so now once we have all these order pairs, we can start plotting that. Remember, all the x values still stay the same. Just have to make y values bigger. So -2, -1, 0, 1, 2. Now again, the maximum value is 109.20. That means we need all the way go out all the way up to 110. Minimum value is 2. So let's say 10 units. This is 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110. Do it by hand, the best we can do is get approximate values, right? So we can't get a perfect graph here. You have to use Excel or other software to get a perfect graph. But no problem, we can live with this. Okay. So I'm going to create different colors so you can see that. -2 is 109.2, so it's almost all the way to the top, almost 110. Okay, so -2, that, and the -1 becomes 40.17. 40.17 is slightly above it. So here. Okay, and 0 becomes 14.78. 14.78 somewhere here. Okay. Now 1 is 5.44. 5 is here. 5.44 slightly above it. And then the very last order pair is 2. So this is 2 here. Here we go. All right, so now connect them. Okay, x-axis is the horizontal asymptote, and it's decreasing from left to right. Okay, if you graph this, it will become okay, f of x 2 times e to the 2 minus x. And then the way how we interpret the y is decreasing, right? We have to do a little bit algebraic transformation here. So 2, we can separate 2e squared times e to negative x, right? So 2e squared, that's a constant. If you do 2 times e squared, that's actually constant, and e raised to negative x. And this negative x, if you reciprocal this, and it becomes over e to the x. So 2 times e squared times 1 over e to the x power, right? So that's why it's increasing, because the base is less than 1. It's between 0 and 1. 1 over e, it's, let me see what they said, 1 over e. It's approximately 0.37. So the base here, 1 over e, is 0.37, approximately. And that's why this is a decreasing function from left to right. And it's not very obvious to detect it from the original function, but once you perform some algebraic manipulation here, you'll be able to tell, why this function is decreasing or increasing in nature. Any question on this? Okay, we can quickly graph this. Okay, I'll put in another sheet. Let me share the screen with you. Okay, here we go. So we put x, and f of x is 2 times e raised to 2 minus x power. So again, we get that, and then we modify a little bit. Okay, all the center. Okay. The value is -2 all the way to 2. Okay. Get that, and then we just let's calculate the result. 2 times exp. Okay. Open parenthesis 2 minus this b3, right? Okay. Then should give us result 109.20. As you can see, get the rest of them, run to 2 decimal places. You will see it should be exactly what we have from the other sheet. And you could just sketch the graph using this. Insert, scatter plot, pick the second option, it give you the graph directly without, without giving you just a point on the curve. And we can get a curve directly by just picking the second option. So this is decreasing from left to right with those 5 order pairs. All right, do you have a question on this? Okay. You can try this, right? In Excel yourself. Okay. Now let's go back to this. This is using a log, meaning how to calculate logarithm. So logarithm is inverse function of exponential function, and in your calculator, you should be able to find a log, log, on either in Excel or the calculator, and you can calculate all these results. Let's say look at 12 log of 79.3. So on the calculator, find log and put in 79.3 in the parentheses. It should give you the result. and this turned out to be 1.90 approximately. Okay, let me just print screen. Let's do some of this. And you should also try this in your calculator. Okay. All right, so for question 12, we have a log of 79.3. And this is actually exactly the calculator input. And once you put in this, you get 1.90. It's 1.899, give you infinitely many decimal places. And if you run it to 2 decimal places, it will be 1.90. Okay. And then 14, very similar, right? And in the calculator, you should also be able to find ln of 21.1. ln is logarithm with base e, right? So this log 79.3 is logarithm with base 10, meaning this log 10, 79.3. By default, if you don't see the number for the logarithm, it's base 10. And here, this is actually logarithm with base e, so 21.1. Okay. Then you put into the calculator as ln. You should also find that directly on your calculator or Excel. Okay, so this turned out to be 3.05 approximately. In a second, I'm going to show you how to do this in Excel as well. And question 16, it's ln of e to 2.1 power. The answer is 2.1, but you can also try in the exact answer should be 2.1 because logarithm base e and an exponential function with the base e, they will offset each other. So these two bases offset each other. Answer is 2.1, and you can also try that in a calculator or Excel. ln e to the 2.1, you get the same result. 2.1 as 2.1, right? Okay. All right. So now I'm quickly show you this in Excel. All right. Another sheet. You share the screen. Okay. So first one is log 79. 3. So the calculator Excel input is log, right? Log 10, right? It's base 10, log 10, and then put in the 79.3. You get a result, right? Exactly what we have. And then second one is ln of 21.1. Okay. And so you put in ln, capital ln, and put in the number 21.1. The Excel will get an answer for you, 3.05. If we run it to 2 decimal places, should be exactly what we have from there. And then the last one is ln of e raised to 2.1 power. Okay, very similar here. So you do ln first parentheses exp 2.1. Okay. And once you input it correctly, the result is 2.1. Okay. Any question on this? How to do in Excel? Okay. Or in a calculator? You should be able to do both, right? Okay. So this is question 12, 14, 16. 17, 20. And again, you just have to, just like how you did it in the Excel project number 2, right? You just have to sketch this, right? Plot all the pairs and try to fit in a linear model or exponential model, or you may not be able to fit in either one of these models. Okay. All right. So you can try yourself, or you can just do a data entry and enter both X and Y, and let Excel sketch the graph for you, and you determine whether either one of these model fits or none of them fit. Okay. All right, so now let's move on to section 2.3. I really want to get started on section 2.3 since it's an application of the exponential function. So let's open the PowerPoint. Now, actually, we just work with one particular formula. It's a formula based on exponential model. And that's why the exponential model is it's the theorem based, right? It's like background information we need to understand before we can look at all those application problems. So let's get started. Okay. Let me share the screen with you. All right, so section 2.3 is on the application of the exponential functions. Okay, and we just mainly talk about the human population growth, right? In the next chapter, you're going to see compound interest. Okay. That's also application of the exponential function. Okay. And to solve any real life application problem using the properties of exponents and exponential functions, why study exponential functions? Because it's widely used, right, in the real world to measure the growth, interest, and decay. And growth obeys exponential functions like, human populations, bacteria, rumors, computer technology, nuclear chain reactions, compound interest. So yeah, we're gonna look at both, right? Human population, compound interest, which is most useful, things you can have in life. And the decay also obeys exponential functions. So we have two different type of models: growth model or decay model. Yeah. And human population growth is a growth model. It follows growth model. And decay model could be carbon-14 dating, half-life, Newton's law of cooling, all those things. And now let's look at the population growth. So this is a formula we're going to use to look at population growth. And again, this model it's like not a most sophisticated model out there, right? But it does the job. Means you can look at a population growth on an exponential using the exponential model. Roughly speaking, if you want to look at it more carefully, then you need to implement some more complicated and sophisticated tools together with the exponential model, because population growth has a lot of different factors, like we just, in this case, we're just based on a natural growth rate, meaning population growth at a certain rate, and it's compounded on an annual basis. And that's what this model is using. Okay. But remember, we also have a lot of different other factors have impact on the population growth, like immigration policies, right? Like the natural disasters, if some natural disaster hits a city or town, the population, will changes, right? Meaning a lot of people maybe will move to other states, and that could also have impact on population growth. Okay. So a lot of other factors, have impact on the population growth. And this one just look at the natural growth rate, meaning annual growth rate. So NT here representing the population at the time t, right? N0 representing the initial population. And then here base E, again, E is approximately 2.718. So for all those subjects who is compounding on a continuously basis, we're using a base E. So population grow at a constant rate, right? And then also population grows continuously. So that's why the base E is being implemented here. And also the K representing the annual constant growth rate. T is the time in years. Okay, so this is basically it's all the elements we needed in a population growth model. So, and any question on this? E is a natural number or Euler number, and E is approximately equal to 2.718. Okay. All right, so now let's just try to utilize this model, right, to determine the population. Some of these elements presented in the population growth model. For example, let's say a population of 1,200,000 grows with the annual growth rate of 1.25%. What is population after 5 years? Okay. So this could be a hypothetical scenario. So we have this initial population here. So this 1,200,000 is initial population. And you try to predict what happened after 5 years in terms of population with this particular growth rate. So we know that N0 equal to 1,200,000. Yes. All right, and we also know the annual growth rate, right? It's presented in the question. So its annual growth rate is 1.25% annual growth rate. K, right? It's 1.25%. Some textbook using R, so it's the same concept. R, okay. Here in our textbook we're using K, so stick with that. So K equals 1.25%. So if you want to turn into decimal, it's 0.0125. Typically, you need to turn into a decimal number for the convenient calculation. And also, we know time t, right? After 5 years, meaning time t here equal to 5. And what we need to find out is NT. So NT, applying the formula, the population after 5 years. Okay. So it's N0 times e to the RT, KT. So N0 is 1,200,000 multiplied by E raised to K is 0.0125 times 5. Okay. Then you can just throw this into the calculator or the Excel, then you'll be able to get the result right away. Times 1E raised to 0.0125 multiplied by 5, closing. Then you end up with this number. So the exact number is 1,277,393.351. And then typically you just gonna run to the, you just typically run it to a whole number, right? So 1,277,393 for the regular running rules. So that means after 5 years, based on this constant growth rate, the population should be around 1,277,393 person, right? Based on this exponential growth model. Okay. So the most important thing here in terms of solving this application problem is knowing what you are looking for, right? Here, looking for the NT. Right? NT is not given. And we know the initial population, we know the annual growth rate, we know the time t, and just list all those given information. Then I will try to find out the population after 5 years. Now let's take a look at one more, right? One more example, example 2. So now what's given here? a population which is 295,000 now has a growth rate of constant of 1.35% over the last 25 years. And what was the population 25 years ago? What are we looking for, first of all? Anybody want to give a shot?
Are we looking for n?
Yes, N0, right? Because they talk about 25 years ago. That means it is N0. So it's like going back 25 years, and definitely, and they also tell us that the growth rate is constant of 1.35% over the last 25 years. So this is constant growth over 25 years. So initial population should be 25 years ago. So that's why we're looking for N0, right? That's unknown. And we know NT because it's presented here saying 295,000 now, right? So that means NT is given. The population after 25 years is 295,000. And we also know the annual growth rate is 1.35%, K is 1.35%. And we also know T is 25 years. So now still, right, we have the formula NT equal to N0 times e to the KT. And you want to throw in the number, and then we're looking for this. We're looking for N0. So if you want to do the transformation before plugging the numbers, that's good. Meaning N0 should be equal to, in order to solve for N0, we need to divide e to the KT from both sides of the equation. Okay, and once you cancel that, then N0 equal to NT over e to the KT. So that's how you solve for the initial population in this case. Now we're going to throw in the numbers. So it's going to be 295,000. That's NT divided by E. The K is 1.35%. If you turn into a decimal number, it will be 0.0135. Okay. Yeah, so this is 0.0135 multiplied by 25. Okay. So now put into the calculator, and then you should get a result. And then calculator input look like this: 295,000 divided by open parentheses E raised to 0.0135 multiplied by 25. Okay, that's how you do it next in the calculator. And let's run the calculation in the calculator really quickly. Let's see if you can have the same result as I have. So this turned out to be 210,000. The exact answer is 210,497.8325. Right. So if you run it to the whole number, it will be approximately 210,498%. 25 years ago, right? That would be the population. So over the 25 years of time, the population grows about 85,000 based on this constant growth rate, 1.35%. And you can also easily get this in Excel, right? Okay, let me show you how to do this in Excel really quickly. Excel, then we can just share the screen. You can do 295,000 dividing by, and here is EXP in Excel, EXP, open 0.0135 multiplied by 25. Okay. And that's the input. And once you put it in properly, hit enter, you get a result. If you run it to a whole number, you become 210,498, right? exact same result. That's what we have. So let's go back. Now, let's move on. Okay, this is example 2. Now, example 3. Okay, according to the U.S. Census, the population of the U.S. was 248.7 million in 1990. Okay, and 2000 it had grown to 281.4 million. What was annual growth rate for the U.S. for this particular period? So now they're looking for annual growth rate. Okay, meaning they're looking for K. K is unknown, right? And everything else is given. And if you want to expand 248.7 million as an exact number, you could do that. But here, since they appear in the same unit, then if you want to keep it as is, that's fine, right? You can keep it as 248.7 million. Just make sure you include a unit in the calculation there. So now here, that's just list what we have here. So we can assume that in 1990, we assume it's where the initial population occurs. So t equals 0 when 1990, right? So when in 2000, when it's 2000, then the t should be 10. Okay, so this is important. We're assuming back in 1990, the t initial time, right? T equals 0. And compared to 1990, 2000 is 10 years later. So for that case, t equals 10. All right. So this is important. So we know that in this case, initial population N0 is 248.7 million. And the population in 2000 is NT is 281.4 million. And between 1990 and 2000, there are 10 years. So time t equal to 10. Okay. So now we have all this given information presented, and we are looking for K. So again, we're gonna first of all write down the formula NT equal N0 times e to the KT. So we're actually looking for K here. So now first of all, let's put in all the numbers into the formula. And we'll go from there. So NT is 281.4 million. N0 is 248.7 million times e to the k. K is what we're looking for. T is 10. So it's 10K basically. All right, so now from there, in order to solve for K, we need to divide in both sides of the equation by 248.7 millions. Now here we cancel the unit million, right? This one get canceled as well. So we end up with the e to the 10K equal to 281.4 over 248.7. And for some of you guys, maybe you want a decimal answers, decimal on the right-hand side. If you want to do that, you can just divide in those two. But just make sure you copy all the decimal numbers from the screen, from your calculator. That means e to the 10K equal to 1.13, 148, 3715. Okay, that's what I find from the calculator. And here we need to get rid of the base. So using this property, which is ln with the base e, right? E to the x, that should be equal to x. We did a similar calculation earlier with ln of e to 2.1, it becomes 2.1. So that means we're going to take ln from both sides of the equation. Ln of that 1.13, 148, 3715. then ln and then base e cancel each other. So on the left, it becomes 10k equal to ln of this. And again, you can put into the calculator, get an exact result from the calculator or Excel. So it's ln of 281.4 by 248.7. And this turned out to be 0.1235. So right here, up to this point, once we get rid of that, we're gonna write on the whole thing, right? 0.1235, 297.94. And very last thing, you just divide 10 from both sides of the equation, and then we get a result. And typically, you run the rate up to 2 decimal after the percentage. That means we're gonna keep it. So first of all, we get k equal to 0.012, yeah, 1235, 297, and 94. And typically, we run it to 3 decimal places. Okay, so that's approximately 0.012. So this turned out to be 1.2%. If you want one more decimal, that's fine. So 4 decimal places, let's keep 4 decimal places, 124. So this is 1.24% growth rate. Okay. Let's keep it consistent since all the problems appear in two decimal after converting to percentage. So it's 4 decimal. It could be 3 decimal, right? It depends on what is it. So typically 4 decimal places, so you end up with 1.24%. So this annual growth rate is 1.24%. Any question on this? All right, let's just look at one more question, right? And then I'll let you go. So example 4, let's say we have the world population is estimated to be growing at a 1.33% per year. If the population is about 7.5 billion right now. Okay. How long does it take to reach 10 billion? So this is actually kind of the real data, right? So about right now, the population is about 7.5 billion. And for all those government officials, like United Nations, they want to forecast, how long it will take so they can prepare for all those resources, like food, shelters, for the humankind. So this is very good. And once you have a very good prediction, then you'll be able to prepare ahead, right? So here we have now we're assuming, for now, we're assuming time t equals 0, right? Then we want to figure out what happened, after certain years, when the population reached 10 billion. We want to capture exactly what year is that. So now we have 2021, and once we know how many years in between, then we'll be able to figure out, by which year the population will reach 10 billion. So here N0 we're assuming equal to 7.5 billion. And then NT is the population after certain years. We don't know yet how many years that is, so it's 10 billion. And we also know the constant growth rate, K, is 1.33% on a yearly basis. So this is 0.0133. And here, the only thing we don't know is time t, right? So we're looking for time t. Okay. So very similar, we're using the formula nt equal n0 times e to the kt. Now throwing out numbers, so 10 billion on the left, on the right 7.5 billion times e to the k is 0.0133. So we are solving for time t here, right? The only thing we don't know is time t. So step 1, we dividing 7.5 billion from both sides of the equation. So we cancel that, and we get a e to the kt e to 0.0133 t equal to 10 over 7.5, 10 by 7.5. That's 1.3333. And you can also simplify as 4 over 3 because both 10 and 7.5 could be reduced by 2.5. So 4 over 3. If you want to reduce, keep it as a fraction, that's okay. And the next step is taking the ln from both sides of the equation. Ln of 4 over 3. Okay, and an ln logarithm with the base e, and an e to any power becomes x, right? Whatever the power is. So these two cancel each other. So you end up with 0.0133 t equal to ln of 4 over 3. And from there, we're dividing both sides of the equation by 0.03133, and we get a time t. And you can just put all these calculations into the calculator or Excel. So let's see what that is. So ln of 4 over 3 by 0.0133. This turned out to be 21.6, right? I'm going to run it to 1 decimal places. So this is 21.6, meaning after about 22 years, roughly speaking, after 22 years, the population will reach 10 billion, right? So now 2021, you're adding 22 years by 2043. In year 2043, then the world population will reach 10 billion. Okay. And that's how you will end up with this prediction about the future, right? Using this population growth model. And do you have any question on this? So for section 2.3, we just deal with one formula, right? Nt equal n0 times e to the kt, and that's a foundation, you know, to calculate any like elements within the formulas. So in this case, we're solving for time t, and it requires some algebraic transformation. So if you guys need some, you know, brush up on the on your algebra skills, right? You can go to, I can recommend a good site for you to review the algebra skills really quickly. You can go to Google and then type in Khan Academy. Now we are doing the exponential functions and then logarithm, right? You can just type in Khan Academy exponents and then logarithm. Okay. And in that case, you're gonna get some, you know, review videos. They have some review videos about exponential functions and also the logarithm functions from algebra. And you can use all of this to brush up your algebra skills if you feel like you haven't touched algebra for a while. Okay. Yeah. So and that's pretty much for today. I will continue. I'll finish section 2.3 on Friday. And also you guys can finish the project number 3 on Friday. Okay. And next Wednesday we'll review, and then next Friday you're taking the exam number 1. Okay. All right. Any question before we end the session?
Professor, I was just going to ask if I could speak with you after class.
Definitely. After everybody leaves, yeah, we can talk. Yeah, sure. Okay. Any other questions? Okay, so feel free to leave, right? Class is over. I will talk to you guys on Friday.
Bye, thank you.
Thank you, Professor.
Bye. Okay, talk to you Friday. So both of you guys want to talk to me about something, right?
I know I for sure do. I'm not
Okay.
sure about
Okay.
Annie.
So maybe let me do this. Let me put you guys in the breakout room so you can talk to me on an individual basis. If you um, does that work?
Sure. Yes.
Okay. I think that's better. Yeah. So just in case you want to talk to me on an individual basis. Breakout room. Yep. Hey, Victoria. So you want to talk about something, right?
Yes. I wanted to talk to you, well, mainly right now about the first lab. I know I made it really confusing and I messed up with the first submission. But I just wanted to, I guess, um,
Redo it.
I wanted to understand why I got the grade I got because you had originally graded me, but then you changed the grade.
Okay, let me take a look at first
And
one.
yeah, sure. I emailed you about it, and I know it's like a whole confusing thing because I had submitted it in the wrong spot. So I
All
know.
right, no worries. So let's look at it. Let me find your account really quickly. So it's that part. Okay, you find it. I'm gonna share the screen with you.
Sure.
And then if you want to improve on it, no problem. I can give you some time to improve. The only thing is, you see, you need to submit it as an Excel file. I think one of the submission was an Excel file. So this is
Yeah.
all.
I understand that.
Yeah. So let's see. All right, this one is grading, and this one is
So,
why you get 70.
so the first
Mhm.
one was the PDF, which you had told me you
Yeah.
have to convert it. So that one was the early submission. And then you told me to put it as the Excel. So the day of I had put it on the Excel file, but that was the one that I had submitted under Excel project number 2.
Okay.
So that's what makes it, that's why I apologize. It's confusing.
Mhm. Okay. No worry. Let's look at why you get 70 on that Excel submission. Can you see your Excel file?
Yes.
Okay, very good. So this is good. This is all good. Okay. Up to this, I think it's still good. And actually, you're missing two graphs. Remember, there are two graphing questions. So you only complete up to all of these are good. And that's why I get 70. And the other two graph is worth 30 points. It's worth more than 30 points, but I feel like, so you see, we have two graphing questions.
Okay.
And let's go back to the Excel project here. The first project we have to graph two couple things. All right, let me open it, show you. And if you want to redo it and then include those two graphs, no problem. I can still take your submission. Just when you finish, I will give you updated grade. But everything else you did, it's good, right? Up to question 7, it's all good.
Yeah, I didn't know I was missing any questions
Yeah, so you're
because
missing question 8 and then question 9. You see,
I
right? Graphing those two. Do you know how to do that?
yes, I did Excel project too, so I did graph before.
Okay.
Let me
Yeah, you can just quickly graph this and then I'll let you resubmit it. No problem. I will open the Dropbox for you and you'll be able to resubmit it. I'll grade it one more time. No problem.
thank you. So the last two problems are just they're included in, of course, the document, right? So the ones I missed.
Yes, you should.
Okay.
Yeah, you just put in the original. Yeah, just put it in the same
Okay.
Excel file. So let me just open. Can you get it done by Friday?
Yes.
Okay, so I'll make it due on Friday. So
Oh, sorry, I didn't realize that I was missing it.
no
So
problem.
I
Yeah,
that's on me.
yeah, I should provide some feedback. I forget to write a note in your account. So in that case, you'll be able to, look at the feedback and
Yes, I appreciate it.
next time I'll try to put some feedback if you did not get a perfect score or maybe your
Okay.
score is low. And
Mhm.
let's say you get anything above 90, that means it's just minor mistake somewhere. So yeah, so you can talk to me, during the class, or especially it's good when you can talk to me on Friday, right? Every Friday during the breakout session. If you want me to check your Excel project before submitting that, you can just ask for my help, and I will just review that for you before you submit it.
Okay, thank
Fine
you.
with me. Yeah.
Okay, well, I will, since there's only two problems,
Mhm.
I'll try to submit it today, but if I can't, I could try to submit it tomorrow.
No problem. Yeah.
I don't want to put it off for until Friday.
Right. Okay. Sure thing.
All
And
right,
then the other two projects, I think you did well, right?
yeah, I think it was just that the first one, I might have missed that there was maybe it was on the second page. I'm not sure why I didn't see it.
Okay.
But yeah, that
It's
happened.
okay. No problem. Not a big deal.
Okay.
Yeah, it's first project, so I probably still get used to it.
All right, thank you so much. I appreciate your help.
No problem. Okay. Very good.
Bye. Thank you.
Bye. Okay. Hey, Sam. So you still have a question?